I now want to look at my first continuous distribution, which is the exponential distribution. And a distribution is exponential with a distribution parameter of lambda, so we do need to know the value of lambda. And in this case, we say x is exponential with respect to lambda. And exponential distributions are defined by the PDF. They're anything with a particular PDF. And that's given by f of x is equal to lambda e to the negative lambda x for x greater than or equal to 0, and 0 for x less than 0. Since we have the PDF of the function, let's try to find the CDF of the exponential distribution. Well, since my distribution starts at 0, I need to integrate from 0 to x of lambda e to the minus lambda t dt. If I integrate this, I get negative e to the minus lambda t going from 0 to x. Plugging in my bounds, minus e minus to the negative lambda x minus negative e to the negative lambda times 0. In other words, 1 minus e to the minus lambda x. So this is how we define our CDF. We might want to know, when do we use this? Well, the exponential distribution is the simplest model we have for the lifetime of an equipment. And it can also give us the time until the next event in a Poisson process. So maybe the time for the next customer to arrive at a service station, or the time until the next bank or investment firm failure, the time until the next earthquake, something like that. So it gives us the time until the next event in some kind of Poisson process. Some basic properties of this exponential distribution. The mean, mu, is given by 1 over lambda. The variance, 1 over lambda squared. And the percentiles, x sub alpha, is given by negative ln of alpha over lambda. So now let's look at an example of the exponential distribution. Let's suppose the useful lifetime, in years, of a PC is exponentially distributed with a parameter of lambda equal to 0.25. A student entering a 4-year undergraduate program inherits a 2-year-old PC from his sister who just graduated. We want to find the probability that the useful lifetime in the PC the student inherited will last at least until the student graduates. So what we want is the probability that it lasts more than 6 years, since it would have lasted a total of 4 years in his program, plus the additional 2 years that it was already being used, given that we know it's already lasted for more than 2 years. Well, conditional probability says this is the probability that x is greater than both 6 and 2. Just the probability that x is greater than 6 over the probability of the thing we know, that x is greater than 2. So let's look at each one of these individually. Let's start with the probability that it lasts for more than 6 years. Well, probability that it lasts less than 6 years would be given by the CDF. More than 6 years would be 1 minus the CDF, which is given by 1 minus e to the minus lambda times x, which simplifies to e to the negative 0.25 times 6. The probability that it lasts more than 2 years. Once again, since this is a greater than, we need to do 1 minus the CDF. 1 minus 0.25 times 2, which simplifies to e to the negative 0.25 times 2. We then divide these. E to the negative 0.25 to the 6th power over e to the negative 0.25 times 2. Properties of exponents say if you divide and they have the same base, I can subtract. So 0.25 to the 6 minus 2, which is e to the negative 0.25 times 4, which is also the same thing that it lasts more than 4 years. So the chance that it lasts an additional 4 years is the same as the probability that it would last the original 4 years. And this is a very nice property here. It's called the memoryless property or the no aging property. So let's take a little bit closer look at this. The memoryless property. This says that the probability that x is greater than s plus t, given that x is greater than s, is equal to the probability that x is greater than t. So this was demonstrated in the previous example. The chance that it lasted a total of 6 years, given that it lasted 2, was the same as it just lasting 4 years. It doesn't have a memory of what's happened in the past, essentially. And exponential distributions always have this property, which is extremely nice.